Hello, ladies and gentlemen, everyone, and I'm so glad to meet you here on this special day. It's Thanksgiving, so iCANX tax is already 33rd, weeks. So we want to appreciate our great, thanks to all these speakers. Actually, I just counted we have more than 90 speakers on this stage, in last 33 weeks. So it was amazing we have this platform to host the world class scientists and deliver the latest result on this stage. So yeah, please follow me to give a plug for all these wonderful speakers. And they deliver their talks and they share the acknowledgement, the serious research with all of us. What a big bonus, for everyone. We stick with high tech and we want to know high tech. We appreciate all of them talks. So as today we're going to have, more and more interesting topics. This week, yeah, the topic is very fun because it is liquid metal. I think many people was first time to know liquid metal is because the famous movie. The movie was named the Terminator. Yeah, the Terminator is a super robot. It can do everything. It's a super smart and super powerful, and it's like everything. But the last, shot, you can see that melt down. Yeah, it's liquid metal. So that time in this science fiction movie, yeah, give a lot of kind of imaginations for the people, yeah, for the scientists. Is that possible we can make this, super robots? Like this liquid metal would can reform into any shape, any functions. Yeah, so yeah, there are a lot of scientists who was working on this. So today we're lucky to have three of them. Yeah, because yeah, we have Xingyu was from South University of Science and Technology. He's doing the research with soft materials, liquid metals with biomedical applications. And then Rao Wei, his group was done a lot of long time liquid metals. They almost done everything in this field. They are one of the pioneer group too. And our hoster, Zhigang Wu, has done very fantastic job for liquid metal. He even make some smart plant. So today he's going to be our hoster. Now, without further ado, first I will introduce, Zhigang Wu, yeah, our hoster here. Zhigang was from Huazhong University of Science and Technology as a super smart guy I met. I think, this was very smart. He has a lot of, fantastic ideas. Today he will be the host and introduce the speakers and ask the questions and to host the stage. So, Zhigang, stage is yours, please.
Thank you, Alice. So it's my pleasure to host this very fantastic topic, liquid metal. So the first topic is Xingyu from Southern University of Science and Technology. Actually, he got his bachelor in University of Chicago and a PhD at Harvard University. At a group of websites is one of my idol actually. Then he joined the National Center of Nanoscience and Technology. He moved to Southern University of Science and Technology in 2018. His research interests include microfluidics and nanomedicine. He was awarded the National Science Foundation of China Distinguished Young Scholars, the Human Frontier Science Program Young Investigator Award. He is the fellow of Royal Science of Chemistry and American Institute of Medical and Biological Engineering. He published a lot of papers. So I leave the stage to Xingyu, please.
Thank you, Zhigang. Can you hear me?
Yeah.
And thank you, Alice, for hosting this wonderful conference. And welcome everybody to Friday Night Talk. And I will tell you about our efforts in combining microfluidics and liquid metal for stretchable biocompatible electronics. So I'm based in Southern University of Science and Technology, a new university in Shenzhen, China. and it's in southern China, so it's very warm, even during this time of the year. If you come to this region, feel free to let me know. So we're recruiting. If you know anybody who is interested in doing interesting research, please send them my way or email me. So our interest actually in this area comes from our effort, a longstanding effort in microfluidics. What I will do today is to tell you first a little bit about our efforts in microfluidics and their applications in biomedicine, and then move on to telling you about our recent fund with liquid metal and microfluidics. So let me see if I could, yeah. So initially, we used microfluidics for various types of biological assays. And the reason for doing that is because using micro chambers and microfluidic systems in microchips allows you to lower the amount of samples dramatically. And then you can increase the throughput by putting multiple biomarkers in one chip. These channels allow you to introduce all the solutions that are necessary for carrying out biological assays, such as immunoassays, which are basically based on the interactions between proteins. So because you put so many of these assays together, that lowers the cost and increases the throughput. That also brings an added benefit of miniaturization, meaning that you can do this in a very small instrument. So this is one of our examples of what we call point of care POCT testing system based on immunofluorescence and immunochemistry and chemiluminescence. So we have an equipment that's about the size of your laptop, and then with a small chip that is basically made up of about 10 components that allows you to automatically control all the solutions that are necessary for washing reaction in the immunoassay. So you can basically put this chip into this equipment, and with the push of one button, it automatically allows you to introduce all the reagents and all the washing steps that are necessary for immunoassays and produce a chemiluminescent signal for your biological readout. So point of care assays like this has become quite important in the age of coronavirus, where you really need to assay for the disease or the pathogen in the point of care setting, where you don't have to go to the hospital. You can do this on the side at personal homes and so on and so forth. So we were initially supported by a strategic pilot project of Chinese Academy of Sciences, and they were very instrumental in helping us industrialize some of our microfluidic technology. We can produce the microchips in large scale. In addition, we're able to build the equipment and the software for the analysis. So this is a very simple video that shows you that we can automatically transfer liquids from macroscopic containers into microfluidic channels. And with the design and the industrialization of all these components, we have an assay that allows us to have multiplex immunoassay in the form of chemiluminescence in the readout. We have worked with a company to apply for the registration under the National Medical Product Administration, which is equivalent to the FDA in the US. And some of our equipments and products are being used in the hospitals. So in addition to being able to manipulate very small amounts of liquids for diagnostic applications, we also use microfluidic technology to pattern cells. So the basic strategy is to introduce mammalian cells onto different parts of the same surface using microchannels, because you can control the width of the channels and the inter-channel distance very precisely. You can control the pattern of multiple types of cells on surfaces. For example, in here, we've been able to pattern HeLa cells, which are stained in green. and 3T3 cell, NIH 3T3 cells, which are stained in red. So these technologies allow us precisely deposit different types of cells on the same surface. Combined with surface chemistry, we're able to make culture of cells that have different types of interactions. By that, what I mean is we can keep the cells completely confined over the course of 24 hours. As you can see, the red cell and the green cells are both confined, and then we can selectively release part of the cell, and then so the cells, part of the cell are moving, and then we can also release both types of cells that at the end of the experiment, both green and red cells are moving. So these types of experiments allow us to not only understand the basic interactions between different types of cells, but also screen for different types of therapeutics. For example, in this particular case, we use this co-culture system of co-culture between neurons and cancer cells in a high throughput format to screen for carriers for small interfering RNAs. So these molecules are able to allow us to reduce the concentration of particular biological molecules, in this case, NGF or nerve growth factor. This molecule is important for promoting the interaction between neurons and cancer cells. So reducing their concentration in the system is critical for reducing the metastasis of cancer, particularly because neurons actually develop this neuronal sprout system, so these fibers that allow the cancer cells to move along them. So in the body, what happens is that with these neuronal fibers, the cancer cells will move around in a process called metastasis and invasion. If you reduce the concentration of NGF, which is critical for the growth of these green fibers from the neurons, the movement of the cancer cells will reduce. Thus, the metastasis or the cancer invasion will also reduce. So we use the microchannels to accelerate the progress and the process of screening for these drugs. If you were to use animal models, it would have taken tens of years to finish the number of screenings that we have in hand. But combining this microfluidic channel with a high content screening system, we can finish the screening that have to be done in vivo that would take tens of years into just a few weeks. And then we are able to screen for reagents that can eventually be applied in human beings. But before that, we have to use animal models. And there are several animal models that we use to test that these carriers are indeed very useful for reducing the invasion of cancer cells. And that the person who pioneered this study was a former postdoc in our group, Dr. Yifeng Lei, who's now an associate professor at Wuhan University. And Dr. Kai Zhang is in the 301 hospital, who helped us, particularly in securing some of these patient samples of cells to do some of these animal models. So with that, we have actually the capability to screen for many types of therapeutic agents. For example, the tools for gene editing, such as CRISPR-Cas system that are lipid encapsulated and with gold nanoparticle. So these systems allow us to precisely release our therapeutic tool with an external trigger, such as a laser, in order to release the gene editing tool for therapeutics. In this particular case, we use the gene editing to cut down the genes that are responsible for developing tumors. In this particular case, we use the CRISPR-Cas9 to reduce to cut down the molecules that are important for cardiovascular diseases. So you can see that using microfluidic system, we can quickly screen for many types of therapeutics. Using these microfluidic system, we can also build live tissues. So the area of building live tissues is called tissue engineering or artificial organ, in which humans really wish to make organs and tissues that are naturally developed, that are similar to or even superior than naturally developed tissues. But the particular difficulty is that there are many types of cells that are necessary that need to be aligned in very well-ordered fashion for us to make artificial tissues. So our effort in this area started about 10 years ago when we tried to think about ways to build blood vessels. Blood vessels are very important because for diseases such as heart attack, which is basically caused by the blockage of blood vessels that supply blood to your heart, or a stroke, which is caused by the blockage of blood vessels that supply blood to your brain. So basically, it's necessary to have artificial blood vessels for some of these cases. So in terms of the medical application, it's really necessary to have these. Another point in artificial tissues and artificial organs is that having the ability to make blood vessels is actually critical for tissue engineering as well. Even though the area of tissue engineering has developed for a number of years, we have very limited access to the types of tissue that human beings can make, or the types of tissue we can engineer. Well, I think one of the limitations is that we are not able to engineer a blood vessel or vascular system, which is important for most organs. The only types of tissues that we can engineer are tissues such as artificial skin or artificial segments, small segments of bone or small segments of cartilage. So these are tissues that are avascular, or tissues that do not have the blood vessels to supply nutrients and take away waste. But most other organs and most other tissues actually require a network of blood vessels in order to function. So from those two perspectives, from the point of a commercial product for patients that undergo stroke or heart attack, and for making artificial tissues, the making of blood vessel is critically important. But the structure of blood vessel is very complex. That's one of the reasons why it's very limiting, very challenging. It's typically, so different types of blood vessels have different structures, but one of the overarching scheme of blood vessels is that it has 3 layers of cells. The innermost layer of cells are endothelial cells, the medium layer are smooth muscle cells, and the outermost layers are typically made up of fibroblasts and neurons. So so each cell, each type of cell is very critical for the integrity of the blood vessel. The innermost layer, the endothelial cells, have to form a complete layer in order to allow the blood vessels to pass through the blood vessel without blockage. So our blood vessel is a very complex liquid with many types of proteins, many types of cells. So they tend to stick and adhere non-specifically on any types of solid surfaces. But the endothelial cells can resist non-specific absorption or non-specific sticking of these proteins and cells on the walls of blood vessel. The green layer, the smooth muscle cells, are also quite important. These are the structural components. They keep the blood vessels open and in their shape. And the outermost layer are the fibroblasts, which are also important for maintaining the extracellular matrix, and the neurons, which are important in keeping the interaction between the cell, between the blood vessel and the nervous system. So having to make 3 types of cells in a very well-controlled manner is quite difficult. Not to mention that between these cells, there are multiple layers of extracellular matrix proteins. So what we realized is that maybe it's not the good idea to directly make a circular structure like that, or a tubular structure like that. Maybe it's good to think about ways to make it simpler, and then try to transform this simpler structure into a complex structure. So if you were to imagine to use an old-style pencil sharpener to peel away this 3-layered structure, if you do it correctly, what you can do is basically decompose this three-dimensional structure into a 2-dimensional structure. And the 2-dimensional structure is nothing but a set of stripes of different types of cells. And that's the structure we know how to make. As I just mentioned, we can use microchannels to deliver different types of cells onto different areas of the same surface. And that's indeed what we did initially. We use a stretch membrane and then introduce these cells on them, and then we roll them up. And what you do realize is that it's a spiral structure we make, but when we increase the number of rows, this structure actually becomes approximately similar to this concentric circle that you see. So this is our initial attempt. But what I want to show you is these are the images of the cells that are stained with different fluorescent dyes. Before folding, these cells are confined to their respective space. After folding, they roll up. This is a cross-sectional image of what this looks like. So basically, we have the innermost endothelial cell, the intermediate smooth muscle cell, and the outermost fibroblast cells. And this actually allows you to structurally mimic this complex structure of the three-layered blood vessel very closely. And so what you realize is that by this rolling step, you can use a relatively simple patterning technology that takes place in the 2-dimension, and then you can roll it up. So this readily lends to scaling up. And one of the ways we do the scaling up is to combine that with electrospinning technology that is able to make small fibers. And these small fibers make holes that are able to allow interlayer communication between these two different types of cells. And when we use biodegradable materials, this type of structures will also allow us to maybe eventually allow the cells grow and repair as the biodegradable material slowly erode away. And eventually we can make an artificial blood cell that are basically the same as that of found in human beings. So we tested a bunch of materials that are biodegradable, that are approved by the US Food and Drug Administration, or FDA, which is the agency that tells you which types of materials and which types of drug and implant you can use. So we use a very popular one called PLGA to make a roll. This is one of the most popular implantable material because the degradation product are things like glycolic acid, which are natural metabolites, so considered very safe. When we do this, however, when we make the roll, as the materials degrade, you see that the innermost tube actually, the inner diameter becomes smaller. So that's actually very undesirable because that would make our blood vessels shrink and eventually block the blood vessel. And the whole point of having the blood vessel is to replace the blocked blood vessel that supplies the blood to the heart of the brain. So that obviously can't work. Then we tried a different one, which is called PCL, polycaprolactone. This is another one, another molecule, another material that's very popular that is also FDA approved. So when this material degrades, what we see is that the inner diameter actually slowly dilates, becomes larger. So this clearly is not very good either. So then we thought, well, why don't we try to put the one that expands inside and the one that shrinks outside and see if there's a way that for them to counteract each other when they degrade. And one of our students tried that, and it clearly did work. So over a course of 21 days, as degradation happens, the inner diameter of the blood vessel essentially keeps the same. So using this strategy, we are able to, again, use electron spun fibers to make these fiber structures and that makes and place cells on them. And eventually, we're able to carry out animal experiments. And then these are the results of the animal experiments. And I feel that for this audience, some of these very bloody surgeries are probably not the best imagery at the moment. So I use the ultrasound of characterization to show you that these artificial blood vessels are indeed working. So if you look at the left column, you'll see a native vessel from half a month to 3 months. And the ultrasound one can simply look for the orange rectangle. If an orange rectangle appears, that simply indicates that the blood is flowing and at the right direction. So our experimental group with the PCl, PL, GA composite, you can see essentially the same with a very elongated rectangle, orange, indicating that the blood is flowing and also at the right direction. But if we only use the PLGA or only use the PCL for this experiment, you can see that after 1 month, the blood is no longer flowing, and that simply indicates that the artificial blood vessel has failed. But don't worry, we do this on the carotid artery, which supplied blood to the head of the rabbit. So most mammals have 2 sets of those blood vessels. So if one of them is blocked, the other one will supply blood to the animal. So we are treating the animal very nicely. So that gives you a flavor of what microfluidics allows you to do in terms of diagnostics, screening, as well as tissue engineering. So now I'm going to go into the fun part, which I think for this audience is what we call metal-polymer conductors. So what I've told you so far, I've always used the microfluidic channel to control aqueous liquid. So about 3 years ago, we decided that aqueous solution is no longer enough. We need to think about some other liquids to work on in microfluidic channels. And of course, we're inspired by many people in the field, such as Dickey, Kramer, and as well as Professor Jin Liu at the CAS. And so we thought that we are probably going to be able to combine microfluidics with liquid metal to make flexible electronics. So this is one of our devices. So this is basically a microfluidic channel where all the channels are filled by liquid metal. And the one that we have chosen here is gallium-indium alloy. And we have used the microfluidic channel to connect a series of LEDs, or light-emitting diodes. So in this particular case, we're using the microfluidic channel as a printed circuit. So in this particular case, you can see that after twisting and stretching, all the LEDs are on. That implies that all the circuitry are through. So we're able to basically use the microfluidic channel now as a substitute for printed circuitry and make it flexible. So this work is initially initiated by Li Xuetang, who was a PhD student in my group and currently at Capital Medical University. Then this work also done by Su Yuchen, who's now a PhD student at EPFL, and Dr. Lei Mo, who is at Guangzhou Medical University at the moment. So that shows you that doing work with us allows you to find your next job very easily. The advantage of liquid metal based microfluidics is that it's fairly low cost compared to other materials that people generally use to make flexible electronics, such as thin layers of gold, such as graphene or carbon nanotubes or silver nanoflakes or silver nanotubes. It's very low cost because the cost of gallium and indium are less than 5% that of silver. And we can do this in large scale. And most importantly, I think it's very biocompatible, as I show you in a little bit. So compared to the other materials, particularly compared to silver, which I think is the most popular material for making flexible electronics, the biocompatibility is much higher. Silver is a toxic metal. It's often used to kill bugs and many things, but it cannot be used in human body. So I think there's a real need for making biocompatible flexible electronics, which is what I will tell you about. So what Li Xue realized is that So following basically the same protocol that everybody else did to make liquid metal-based microfluidics. So here I want to stress that we didn't simply inject liquid metal into microfluidic channels because the surface tension in liquid metal is extremely high. You can only inject liquid metals into millimeter scale micro channels. Under normal conditions, you can't even go to less than several millimeters. So if we want to use micro scale or even nanoscale channels to introduce liquid metals, this is one of the ways. So what Li Xue does is he used a solvent to mix with the liquid metal, and then under ultrasound, the liquid metal becomes disintegrated into very small particles we call liquid metal particles. So it becomes an ink. And then we print it on the surface using a bunch of technologies such as screen printing, soft lithography. Zhigang has mentioned that Professor George Whiteside was his idol, and coming from his group, we understand the technologies for soft lithography very well. And using polymer casting, you can transfer the liquid metal onto a different substrate. So we can control the condition such that we can achieve entire transfer such that the liquid metal can be transferred to the completely transferred to the transfer layer, or we can use partial transfer depending on a variety of factors, choice of materials, speed at which you pull, and things of that sort. You can achieve partial transfer in which you can get both the top layer and the bottom layer patterned with liquid metal microfluidics. I should mention that this is actually not trivial in that, as I mentioned, liquid metal, particularly gallium, when you make it into small particles, very quickly, there's a layer of oxide that forms on the surface of this liquid, of these particles. And the problem with that is that the gallium oxide is non-conducting. It's an insulator. So even if you put them together, stack them into a microfluidic channel, that will not be your conducting. That will not be your conducting path. So you have to break this oxide layer in order to achieve a conducting path. So the way to do it, there are several ways to do it. In this particular initial case where Li Xue demonstrated, we call a vertical stretch, where you pull this substrate, the top substrate off of the original substrate in which the liquid metal ink is patterned. So what happens is that in this matrix, when you pull, the gallium oxide actually can break very easily. And it only can break easily in the case of encapsulated polymer. So that's why we stress that we have to encapsulate the liquid metal in a polymer matrix. That is really critical for the breakage of the oxide layer. When there is an encapsulation, the PDMS only has to undergo a very small deformation for the gallium oxide to break. So this is what we call a vertical stretch. Let me show you some of the applications that we can achieve with this technology. So what Li Xue realized early was that you can actually do this at very large scale. You can pattern them completely on a glove, and then this is when we are testing the conductivity of the circuitry as your finger is bending, either slowly or very quickly. So that shows up as on the screen as the change in the conductance as you stretch, as you bend the finger and stretch the electrodes, the resistance becomes larger. So that allows you to quickly determine the actions of your fingers using this technology. So here it explains to you that we can do this not only in just one finger, but in multiple fingers. And we can convert this glove with MPC into a keyboard such that we can type using this pair of gloves without having to use the QWERTY keyboard. The way that works is to imagine that we have one of these resistors on your left pinky, and then depending on how the left pinky bends, that correlate to the letters Q, A, Z on your QWERTY keyboard, which are basically the 3 letters that you normally type with your left pinky on the QWERTY keyboard. So of course, the reason why Li Xue invented this is for me to help him write the paper more quickly. He was complaining that it was taking me too long to help him to write the papers. Typically, he writes the draft and I write it, and then I send it back to him. But at the moment, I was traveling quite a bit, and I was telling him, well, there's no way that I can write a paper using my laptop on the plane because the space is so tight. It's very uncomfortable. And then he gave me this pair of gloves and said, well, now you can work everywhere. You don't have to complain. Then after that, we were much faster in writing, particularly his papers. So I told you about the vertical stretch. Some of the audience may think there must be a horizontal stretch. Indeed, there is. So this is another way to break the oxide layer, also pioneered by Li Xue. So what he realized is that you don't necessarily just have to do this vertical stretch. Sometimes you don't want to peel the pattern off. And what do? So what he realized is that you can also to stretch this horizontally only in the presence of a polymer. So again, I stress that we have to use the metal in the polymer matrix in order to quickly break the oxide layer in order to establish a conductive path. This is critically important. So here are the scanning electron microscopes that help us understand the mechanism. So the middle column are the cases where the liquid metal, the particle inks are encapsulated with the polymer. And after stretch and return, you can see that there's a general smear. So basically all the metal balls, they have been broken. So that's when the oxide layer break and gives you this conductive path. In the right column, you can see that this is the case without polymer. Even if you stretch and then let it relax, basically the structure of the ink and particles are the same. So the reason is because you have to have this matrix to help you pull this oxide layer apart, because the oxide layer is relatively brittle. If you stretch it in the matrix, it will destroy the oxide layer and gives you the conducting path. But if you're just stretching the isolated particles, they don't really feel the stretch. They are not strained at all. So when they return to its initial position, they're essentially the same as when we started. So there's no conducting path. So using that, what Li Xue realized is that you can actually use this technology to do a very large scale patterning and also pattern on very strange surfaces. So you can do very large scale patterning and you can pattern on the glove. And there is an LED light in here. And even after you pull your finger twice as long, you can see that the LED is still lit. And then you can pattern on curved surfaces and spherical surfaces. So this is a balloon in which there is a circuit that is connected to a light. You can see that as the balloon is being filled with air, the light is still lit. So that shows you that patterning on soft surfaces and also large scales can be quite straightforward. And then Li Xue had the idea of patterning on a T-shirt. So on this T-shirt, basically, this T-shirt can become your ultimate wearable machinery. So Alice hinted earlier that everybody can potentially become a Terminator using liquid metal. So this really is, I think, becoming your solution because you can build all your devices onto the T-shirt. You can have your strain sensor that allows you to sense the strain and detect motion. You can build in a heater. Of course, you don't need it in Shenzhen. It's so warming here, but I understand it's getting very cold in Beijing at the moment. Maybe with the heater that's covered on the all surfaces of your T-shirt, you don't need your very thick coat to go out to embrace the snow in Beijing. And then you can constantly detect your electrocardiograph using this T-shirt. I think for most people, most young people, you probably are not aware that the heart attack actually kills more people than cancer. So it's actually the #1 death worldwide. So for older people who have cardiovascular problems and such as past heart attacks or hypertension, having the constant monitor of the condition of the heart, having constant ECG is actually critical. And for people who are interested in sports, particularly sports that are very strenuous like marathon, having this type of long-term monitor is also quite important. My understanding is that every marathon seems like there's always at least one casualty. Some people die from marathons because of their system simply give out. So if you have constant ECG and provides a warning before your body collapses, that would save lives, of course. And then for electrochemical biomonitoring, monitoring of sweat components, I think this is an emerging area where it will be very important. Remember what I told you about our efforts in using microfluidics for diagnostics. We're very interested in using microfluidic channels to diagnose different types of biomarkers. So this having to combine ECG with biomarkers that will provide an even greater amount of information for the bodily health. So that tells you the vertical contact, vertical stretch. So sometimes you can't do vertical stretch, you can't do horizontal stretch. So what do? So Lishi has, of course, always has solutions. So in this particular case, he came up with a method to break the oxide layer without any physical contact. In this case, he uses a polymer called polyvinyl pyrrolidone. So this is a polymer that is very often used in many fields, from medicine to pharmaceuticals to makeup materials. So PVP is a material that has the following characteristics. So with water, so it readily absorbs water. With water, it swells, and then it can also dry very easily. And with drying, with water leaving the system, it shrinks. And this process is fully reversible. So with water, it swells. Without water, it dries. So Lishi thought, well, why don't we coat the surface of the metal, the liquid metal, with PVP, such that with different drying and wet cycles, the swelling and the shrinkage of the polymer hopefully will be strong enough to break the gallium oxide, to break the gallium arsenide surface to make a conductive path. So this is indeed what happens. So this is the 3 cycles of wet and dry. So this is relative humidity 100, relative humidity 4.5%. You can see the conductance gradually increase to a plateau after 3 cycles of wet and dry. And of course, where Lishi was very careful in using SEM, or scanning electron microscope, to characterize the system and see that indeed after the wet and dry cycle, almost all the isolated liquid metal particles had merged together. And using this, you can build very complex printed circuitry. Circuitries that have multiple layers, that have patterning not only just on one side, but have pattern on 2 sides. So these complicated devices can be made fairly easily. And you can see that you can stretch and they recover completely. And then Lishi has used them for blood oxygen detection and also heart rate and temperature monitoring. So this is one of such a device where he put on his arm. If you blow it up, you can see that this device, this multi-layer device, actually attaches conformally to the surface of the forearm. And then that device allows you to do 4 readouts at the same time. You can detect wrist flexion. You can look for blood oxygen saturation, detection of heart rate, detection of wrist temperature. Again, we had a perfect solution for COVID monitoring, blood saturation monitoring, of course, for patients that are infected with COVID-19, very important. Many of the patients die because of very low blood oxygen saturation. And then everywhere you go these days, you have a wrist temperature measurement. And with our device, you don't have to show them your wrist anymore. You can just connect this to your smartphone and then send the information to the guard before you even enter the building. Anyways, using this polymer-based system that allows us to break the oxide to establish conducting path, allows you to make very complex multi-layered devices. Next work by Li Xue is using MPC for an electrical tattoo. So in here, the reason why he wants to make electrical tattoo is that he really wants to make devices that allows you to wear it for a very long time. Our devices before this are typically not so comfortable and conformal to put on, such that you can go about your daily business without even noticing it. So that's our goal here. We really want to make a system that allows you to go about doing your daily business. So here, if you make it so thin that it becomes part of your body, like a tattoo, you barely notice it. So in this particular case, Li Xue, with the help of several others, co-workers, again, Lei Mo, as well as another student, Qi Jie, had pioneered the use of different polymers. So this is styrene, butadiene, styrene block copolymer. So this is basically like a rubber. It's basically like an artificial rubber that's used for making your car tires. It's very strong, but it's very elastic. It allows you to achieve a very thin layer without having to add without add any additives. So we call this multi-layered electronic transfer tattoo because it has to be initially made on the surface, and then on the sticking surface, the patterning surface, and be transferred onto the back of your hand. So in this particular case, we have transferred them onto the back of our fingers. The back of our fingers has many ridges and troughs, so it's very difficult for your typical flexible devices to come into complete contact. So if you make the material very thin, it has the ability to come to almost complete contact with the back of your hand. So in this particular case, I stress almost complete contact, because if you blow up the side view, you can see that because the crevice, the crease actually go very deep onto the hand. It's impossible to make your membrane go completely to the bottom. But having a very thin membrane actually allows you to measure the deformation very accurately, as I show in this particular series of image. If there's very poor contact as you flex your finger, the yellow part, which is the part that we make the flexible electronics, it barely moves, right? If it doesn't attach very well, so if it initially attaches like that, and once you change your finger, it detaches that's also no good because the deformation will no longer, so the maximum deformation actually takes place at the suspended part. There's barely any deformation here, so you will not be able to detect the deformation very well. Only when you have this case, when you have your membrane that goes very deep into the crevice, do you see when you have this change in your finger movement, do you have maximum deformation? So we call this effect crease amplification effect. Again, this is also very well illustrated in this particular case, where when you change your position, the posture of your fingers, the part that gets strained most is the suspended part, and you have to have the suspended part close enough to the bottom of the crevice in order to achieve this crease amplification effect. And we did test this using the METT, which is very thin. You can see it conformally contacts with your fingers. And we can also make this using EcoFlex. So EcoFlex is the major material for silly putty, for those of you who know what it is. It's very flexible. And then you can use PDMS or polyurethane. You can see that our METT outperforms all the others because it's very thin. And it allows you, and it also sticks to your skin very well. That allows you to have this crease amplification effect. So Lishu was able to make a 7-layered heater using this technology, and this heater can be stretched as we show. And this tattoo can capture the motion very, very easily and accurately. So if you stick the device on the palm of your hand, if you want something that allows you to capture the motion of your hand and transfer and possibly transfer that motion somewhere, or you record the motion and try to understand your motion, it's very important to be able to detect the motion of all these joints. The PIP are the joints that are these joints, and the OAS stand for the open angle between your fingers, and the MCP, and then the wrist motion are very important. So having the ability to detect the motions in these areas allow you to almost completely capture the motion of all the fingers in your hand, and then hopefully that will allow you to use that to precisely manipulate a robotic hand, which is one of the applications that we'll show later. So you can see that using one layer that allows a maximum detection of changing resistance. As you add the number of layers, the sensitivity drops. But what this shows you is that at 5 layers, you can still have detectable sensitivity. And then you can, so that's the angle for between fingers that allows you to have detection of fast and slow motions. And this is simply a technology that allows you to detect the temperature of the back of your arm. So here's a demonstration for using the transfer tattoo to control the robotic hand. It almost allows you to have exact motion. There's a slight delay in the motion because we want to, we've set it that way. You can set it to be completely synchronous. Again, here, these transfer tattoos allow you to have these motions very precisely. And we also can make self-healing electronics based on MPC. This is work by Mole and Chije in our group. And then, so Mole and Chije thought that we can use diodes to break the oxide layer and then embed that with SBS. And once you stretch, you'll get a conductive material. And this allows a very significant stretch. And if you break it, don't worry. under very slight heating, it can self-heal. So the original conductivity is almost the same as the self-healed conductivity. And there are many ways to do the patterning. And we also showed that biocompatibility is very good. First of all, if we embed it in the liquid metal, there's very little leaching. So the pure liquid metal, lots of leaching. If you embed it in SBS, leaching is is prevented to a large degree. And the concentration of gallium in human ions in these organs are kept to a low amount. So it's nanogram per gram, so less than 100 parts per billion. You can grow mammalian cells on surfaces of SBL and liquid metal. They're essentially the same as PDMS. And then we can also look at biomarkers in serum that respond to inflammation, such as CRP or PCT. If their numbers increase, that would mean that these metals are toxic, but they're not raised, so indicating very good compatibility. And then these materials can be used as glue. So this is the LED that can be stretched. You can see under stress conditions, the LED are still lit. So in the final few minutes, I will tell you about our efforts, our recent efforts in making liquid metal or the MPC-based electrically connected organs and tissues. So this comes back to our effort in making three-dimensional artificial blood vessels. Let me remind you that we make blood vessels by using microfluidic-based painting and then rolling of blood vessels that have three different layers of cells. So Shiyu, Hanchen, and Ding Li were the students that pioneered this part of work. And we were helped by, we collaborated with Professor Zhang Yan at Fuwai Hospital, which is the premier cardiovascular hospital in China. So with flexible electronics and the ability to make artificial blood vessels, we have to make electronic blood vessels, right? Blood vessels that can be electrically connected. So here we use the MPC electrical circuitry as the substrate on which to pattern our blood vessel related cells. And you can recall that we have three different types of cells: endothelial cells, the blue one, smooth muscle cells, and fibroblasts. And it's critical to make sure that we have a complete and full layer of the endothelial cell. So and that's where the electrical signal comes in to be very important. So here are the result of the curled up structures. And these hemolysis experiments show you that these gallium indium alloys are non-toxic. And these cell growth images indicate that they can grow very healthily. And then we apply initially a direct current at a fairly low voltage. What that does, which is already shown by other people, is that it will actually accelerate the growth of endothelial cells. So this is the layer of cell that I told you that we have to have a complete inner layer within the blood vessels. So this is an experiment that shows the proliferation. The higher the voltage, basically the more the growth of the endothelial cells. And here is what people call gap closure experiment that tells you how quickly the endothelial cells can come together to form a complete monolayer. You can see that here 15 millivolts per millimeter is more than enough to achieve this. And then we did this not only on the flat surface, but also on surfaces that are curved, that are rolled up. Without electrical potential, the two cells are not hitting very well. With electrical potential, the cells almost achieve complete healing, complete monolayer, exactly what we want to achieve. And in this case, we show that using this these electrodes, we can carry out what's called electroporation. that allows you to do a plasmid transfection. So this is basically another word for introducing gene therapy locally. So gene therapy, of course, is to introduce exogenous genes, to introduce foreign genes into the cell. Typically, mammalian cells don't take up foreign genes. When you do electroporation, what happens is that at high voltage, the membrane of the cells temporarily break. And then that will allow the plasmids to enter the cell. So these genes can enter the cell and start to function. For this particular case, we introduced a gene that encodes the green fluorescent protein. This is a protein that once enters the cell, it would brightly fluoresce. So that's how we know that the gene is introduced into these cells. And when we do this on the blood vessel, you can see that the GFP layers are indeed fluorescent. And you can superimpose that with the endothelial layer, the smooth muscle layer, and the fibroblast layer. And you can see that the endothelial layer is in the innermost part of the blood vessel. And of course, with any biological, biomedical experiments that aims at a particular disease, you'll want to go to the animal model to further test it. And here, again, Professor Zhang Yan was instrumental in helping us to set up this animal model because it's very difficult to do these rabbit-based experiments. Our blood vessel experiments that are aimed at replacement of cardiovascular blood vessels typically needs to be between 2 and 6 millimeters in diameter. But if you were to do this experiment on mouse rats, even their largest blood vessels are smaller than that range, so it's impossible to do that. So the ideal animal is to use rabbit. But rabbits are particularly finicky. They easily die, and their surgery are not very easy. So Professor Zhang was very instrumental in helping us find the right person to do that. And the in vivo experiment are very successful as well. After sewing them on, you can see that the inner diameter keep a constant. So these are CT, the X-ray images of what happens after the blood vessels are sewed onto these animals. So that shows success. And after the animal are sacrificed, you can see that the inner tube, in the inner space of vessels are through. So this is exactly what we had expected. Another project that we try to use in order to get a good vessel is to use the stent. In this particular case, it's an extravascular stent. So compared to the typical stent, which are intravascular, expands the blood vessel. Here we use a stent that surrounds the blood vessel. Again, we use electroporation to introduce a foreign gene that allows us to have a complete inner endothelial cell. The CD31 expression is a cell that allows you to have this inner membrane. So the particular plasmid that we use is displayed in here, in which TIMP3 is a critical gene that allows us to grow the inner endothelial layer while holding back the growth of the smooth muscle cell to keep and hollow lumen. So here are some images that provide further evidence. So basically, anything above the dotted line should be as thin as possible. And with the electroporation and the stent, we can achieve that. Without the flexible electronics, we're not able to achieve that. And again, the toxicity is very low. With the gallium, you can go to very high, 600 milligram per kilo. You can still, the animal is still very healthy. But in here, you can also do planting surgery in animals. So the last story I want to tell you is we also use this liquid metal-based microfluidics to make electrode arrays. So these are done by Dong Ruihua. So he was able to make microelectrode arrays that can interface with the brain. Of course, they are also highly flexible, similar, but their electrical properties are similar to your typical micro array electrodes, and you can grow neurons. So these are neurons that are isolated from rats, and they can grow for a very long period of time. And you can record electrical potentials. And we're hoping that eventually we'll be able to not only record but also stimulate, and then even building complex organs like neuron, like small tissues in the brain. So I think that's all that I want to tell you about. I want to thank our collaborators, our funding agencies, and mostly our co-workers, the people in our research group. They have really done a great job. And so this is taken in Shenzhen. This is a typical day in Shenzhen. So everybody is wearing t-shirt, and we hang out on the beach. With that, thank you very much for your attention.
Thank you, Xingyu, for your wonderful talk. So we come to this question section. So the first question is Professor Xingyu Jiang, 3D artificial blood vessel is a very smart idea. Can you give us some details of its mechanical properties like strength, stretchability, and so on?
Yeah, that's a very good question. I don't have the results, but we did test the mechanical properties in particular because blood vessels have to withstand fairly high pressure. So we used at least 3 times the maximum human blood pressure, and our blood vessels can withstand those pressure. And from some of our in vivo experiments, you can also see that the inner diameter of the blood vessels are essentially the same as the native vessel. If the mechanical properties are much weaker, what happens is that when the blood flows through, they will expand like a balloon.
Yeah.
So you don't see that. So that shows you that the mechanical property is quite good.
Okay. The second question. Thanks, Professor Jiang. Wonderful talk. We and also layer on metal affect its electric function.
The thickness of the oxide layer. So we haven't measured it. We haven't specifically measured it, but because people have reported the thickness. I think it's about 2 nanometers. We haven't carefully looked at different liquid metals. We know that for mercury, I think it's much thinner. Sometimes it in certain, because mercury oxide is fairly unstable. But for biomedical applications, we absolutely cannot use mercury because it's highly toxic.
Then the comment is how different is for different liquid metals. You know, we will have a
we haven't characterized that. Maybe the next speaker, their group has done quite a few characters. Maybe she will be able to answer that.
Okay, we come to the third question. One question for fabrication of liquid metal electrode. How about the size and precision?
That's a great question too. So in our case, we use either screen printing. The screen printing resolution is fairly low, tens of microns. But with stamping and transfer printing, we can go down to about 5 microns. We haven't had to use anything lower than that because all our experiments are, at the cellular level. So you don't really have to go to that low. But in the literature, people have reported as low as, I think, tens of nanometers.
Okay, thank you. Now, the fourth question is, thanks, Professor Jiang. Very impressive talk for the e-title. So you must know relative work in Professor Nanshu Lu's group. Yes. Can you give me some comments on these 2 different approaches?
So yes, Nanshu's work is also brilliant. So I think we use different approaches. She uses a very thin metal layer with serpentine design to attach to the surface. I don't think she has shown multi-layer structures. I think at least the way I understand it now, maybe I'm wrong, but the way I understand it now is that with our system, multi-layer structure might have an advantage. But if that's incorrect, somebody feel free to correct me.
Okay, the final question. If we revert PVP, will the material become insulated again?
That's a good question. The answer is if you just wet it a little bit, no. But if you add a very large amount of water, PVP is actually slightly water soluble. So if you etch away the PVP, then the oxide layer can sometimes reform it under stretch conditions, and then you can have a conducting path. But that's a very extreme condition.
Okay, actually, that's one question I forgot. I should be in the sixth question. So on page 34, why the 0 to 3 structure is conductive?
34. Okay, let me find
34.
that page.
Yeah.
0.
Sorry,
What was
0 to 3 structure.
the 34? Page 34. Why is you mean why? The question is why is this structure conducting?
Yes.
So the reason is because SBS is a rubber. So if we heat it, it becomes the liquid again, and then under that condition, the liquid metal can come together, and also under So basically, the polymer actually reconnects the broken liquid metal. So that's a short answer to that question.
Okay, it's a nice approach. So as usual, so we will deliver the certificate. So actually, the electronic one. So you are. Thank you for a wonderful talk. So actually, we are making is hard copy. If you have time, you can go to Beijing to collect it.
Well, yes, I will come to collect it. Do I have to? Can you send it to me?
Yeah.
Do I have to come to Beijing to collect it?
Yeah. So we come to this panel discussion. I think liquid metal is a very fantastic topic. So I just ask you, so what do you think this is the most fantastic issue or one fantastic topic when you're doing this liquid metal research?
Maybe let Professor Rao answer first if she wishes to. Or is Alice talking? I think she's
yes. Yeah, I'm talking. So,
okay.
Xingyu, yeah, actually, yes. I will deliver that certification to you.
Thank you.
Don't worry about it.
Okay.
Okay. Raoui, could you please turn on your microphone? Yeah. Okay. Xingyu, go ahead to answer that questions. Wait, just.
I'm sorry. I already had. Can you repeat the question?
I think yes. I think Wei, can you unmute your microphone?
Yeah, it's already worked out now.
Yeah. Okay. That. She think you're the best person to answer this question. What is the most fantastic point for your for liquid metal? You think? Can you hear me well?
So the most fantastic application. So maybe I'll answer that question first. So for me, of course, I think it will be interfacing with human being. either outside as a tattoo or as a wearable device. More importantly, inside, I think, to interface our tissues. As I shown with the electronic blood vessel, I think with that, we'll be able to go further to make electronic hearts, electronic, liver, lung, eventually connecting your brain with electrodes. And we are hoping that eventually the system will be so advanced that the brain-machine interface will totally change the way you communicate with the brain. So currently, the way we study is via our eye, our ear, changing that into electrical signal and making a memory in your brain, right? I think in the future, we may be able to directly write electrical signals into our brain. In the future, maybe you don't have to go to Chemistry 101. You will download Chemistry 101 onto your brain using our flexible electronic system. Don't you think that's possible, Alice?
Yes, I like that idea. Actually, yeah, weeks ago I gave a lecture was from Alice to Alida. Yeah, I think exactly the idea is like this. We make a lot of, electronic in soft materials, and we use electrode maybe by liquid metal or any other kind of this soft and stretchable, material approach. Yeah, later we can directly connect the signals. Yeah, you can either to deliver it or you can either to rewrite, rewrite all these things. I think that's very possible. Yeah.
I agree.
Okay. Rao Wei, how about your idea for this?
Okay. Actually, for me, I think liquid metal always bring us a lot of surprise. Our background is thermal engineering. So when we do some basic thermal science, we usually find some novel phenomena of the liquid metal. And based on some common experiments, liquid metal show some, if we change some parameters, liquid metal will show different phenomena. For example, when we do some deformation experiment, if we change the parameters by the adding different ratio of aluminum, they will show some color change property. And for us, I think the most exciting thing is to achieve the smart robot, such as the Terminator 2. Yeah, they can do everything. They can achieve the liquid and solid transition freely, and they can go through the wall, and they can do the self healing. I think this is a great goal for my team. Yeah.
Okay. Actually, I think these wearable electronics and also these fundamentals is both very, very, very interesting topic. I want to ask you, what is the most challenging issues for future liquid metal research?
The most challenging. I think I can answer this question from two aspects. One is from the fundamental research. I think for liquid metal, especially for the micro or even nanoscale research, there are a lot of questions can have not been answered yet. For example, how to achieve the surface tension and the wettability, very smart regulation, and how to fabricate some hydrophilic or hydrophobic substrate for the liquid metal. Yeah, and so on. And from the application aspect, to achieve the soft robot such as Terminator 2, I think it is very important to set up a very complex and a very smart the external field regulation system to make the robot stand run like human being. Yeah.
So I agree. I agree with Wei on both her points, and I would like to just add that I think a big challenge is application. We have to find. I think we have to find the right application and find the right application such that liquid metal will eventually be used. Otherwise, I think we'll be just have a bunch of interesting demos without real application. We have to really make what we envision happen. I think that will be critical for the future of liquid metals.
About application, so you mentioned this MP, but I want to ask a first step. What you think the most point or some application can be have we can have a nearly commercialization?
I think Wei is better at answering this too.
Yeah, actually, we have already achieved some commercialization of the liquid metal-based applications. So, for example, in the thermal management application, we have developed many different kinds of the convective cooling system. And several years ago, they have been already go to the market for the chip or LED cooling. And in the electronic printing area, we have already developed a different kind and system with different principle for the with a different character printer. And this printer some have a very fast response to fabricate PCB in several seconds. And this new printing method, I think in the future they will change the electronic printing method. Yeah, and in the third aspect, I think the liquid metal-based biomaterials or some exoskeleton, such as Professor Jiang did what Professor Jiang did. Maybe in the future, part of the applications can go to clinical trials. Yeah.
So my opinion is that the biomedical related applications will be the most will likely to be the most successful in commercialization, because the liquid metals I think have a very clear advantage compared to other types of electronic systems in both toxicity and flexibility. But again, here we're of course competing with other technologies, with the gold and with the silver and the graphene and so forth.
So Xingyu, do you remember a few years? I think it's more than 2 years ago. Whiteside talk about microfluidics. What mentioned was a key application of microfluidics. So I also ask both of you too. So what's the application, key application of liquid metal, do you think?
Yeah, so I think what I was talking about, I was talking about earlier about electrically connecting all tissues and organs. I think liquid metal might be the best choice, considering all the parameters such as biocompatibility, biodegradability, and the ability to stay within to come with polymers to almost adhere to almost any tissue. So I think that will eventually be the killer application, but that has to be realized. I think we're working very hard towards that.
Do you have any idea on this key application?
The key.
Key application.
Killer,
Important,
killer
the
application.
most promising application for liquid metal.
For liquid metal.
Yeah.
So for me, what I expected is the liquid metal-based electronic printing method can replace current, for example, the chemical deposition method someday in the future. Yeah, because this method is pretty fast and it do not any post-treatment process and have show many and they also show very good stretchability even under some ultra environment. But I think that currently we still need to solve some critical problems for this method. Yeah, because the chip problem currently is still the bottleneck problem for China. So we do hope the liquid metal-based printing technology someday can change the situation.
Yeah. Very good, very good. Yeah. So actually, Zhigang, yeah, as a audience, yeah. So yeah, I think the killer application for the audience, most of the public was looking for liquid metal is to make something smart like the robots. Yeah, like even make something more smart than we imagine. So like your job, you make a smart plant, right? Yeah. Could you introduce a little bit about that? How you think about liquid metal to link the vegetable, or the plant?
Actually, recently we're thinking to make some more big world. So now we all mention the IoT, the internet connect everything. Actually, we try to measure the human, try to measure the connect with this medical equipment, but we forgot we have many things on the universe. We have this plant. This only occupy most of surface of our Earth. So if we can connect this plant connect to the universe, then we can maybe have the chance to reshape our whole world. For example, if we connect them, we can control the weather and even we can regulate our climate. So I think we have a huge space in this kind of connected with plant with, and also if we can connect animals and the plant itself, so we'll totally change the economy of this Earth. I think we have a huge space here. Thank you for that.
Okay, yeah, I like that idea. I heard your story, last week at Shenzhen. I think Xingyu gave us a very nice topic. Is connect all these, bio issues, right? Linked by the, liquid metal, and we will give us an overall picture for fabrication of match. But your job is another kind of direction. You link with all these things we normally forgot, right? Enough like a plant, like this, any IoT things, right? Like some especially the physical, the object they can link with everyone. Yeah, I like that idea. I think the smart plant and all these things will really work. Make the world change, makes the climate change, right? Make another ecosystem. Yeah, it's very, very great. We still have several minutes. Yeah, now we think we can ask another questions. Actually, recently will be the season for the students to apply for graduate school. Yeah, so most of the students want to know the supervisor's thinking. Yeah, how you pick up the students. Yeah, how you choose, the students especially in this kind of very advanced field. So yeah, maybe Zhigang, you go ahead first to tell something. Yeah, your experience pick up the students, the smart students in your group.
um, Actually, I think before when I was in Sweden, were easy to pick couple of students because most students, if they want to do this job or want to pursue a PhD, he think about very carefully which kind of topic is what he truly like. If he or she think is your right topic, he will do very good work. But after when I moved back to China, I think a bit change a bit of situation. The student, most students, they're very smart and also very hardworking, but they are very confused for what topic they were devoted to. So we try to look for a smart student, but after a few years, I think we should find the best student. They should be very keen to what he did or what he is doing. So I think this is my experience on the graduate.
Okay, very nice. But you have a teaching in Sweden that time, totally different type of students, right? Applications. But we here, yeah, is another kind of style. So, Raowei, yeah, could you tell us something how you pick up the students and CAS, Chinese Academy of Science? Yeah.
Yeah, as for me, firstly, I would like to choose students who is open-minded. I think this characteristic is really very important for our lab's work because my major is thermal engineering. So most students they focus on the thermal heat and mass transfer. So if they focus on this area, they could not do some interdisciplinary work very well. So I think if they want to do the liquid metal research, they have to get ready to learn everything to learn biology, to learn materials, to learn some related chemistry, and so on. So this is the first point. And secondly, I like to choose students who like to think. You know, Chinese students they always like to do the simple wider ask them to do. They do not most of the time they do not have their own thinking. So if you want to do some frontier study, I think the independent thinking ability is most important. And thirdly, I think the students have to have a very high passion for science.
Mhm.
I think they should have the idea to do something to change the world, not to do something to follow others. Yeah, that's the three
Wow.
factors I would like to illustrate.
What a nice word. I like that. Yeah, you need to change the word, right? Not just follow others. I think this like Xingyu, that time you choose by George Whitesides, right? Why he choose you? Because you want to change the world. Okay. Now, the question is for, yeah, how you pick up students. Xingyu,
Yeah,
yeah.
so I basically only have one criterion. So I ask the students if they are ready to learn new things. I think that's very important, particularly for our group. We're always learning new things. If the student is only comfortable with the knowledge he or she has already acquired and is not willing to go beyond what he or she has studied, I think I cannot possibly provide guidance to the graduate work. So I always ask students, are you willing to learn what you haven't learned before? Are you willing to teach yourself new things you haven't even thought about before? So if their answer is boldly yes, then yes. If they have some hesitations, slightest hesitation is a no.
Okay, that's very interesting. That's the next question I try to ask you, but you already answered. Because normally if you ask that, the students say yes. Yeah, but maybe the body language tell you some difference, right?
That's important, yes. Yes. You have to not just listen for the answer. You have to look at the response, you know.
Right.
Some students are like, yes, then that's no.
Because they never think about that. They always do what you tell him to do, right?
Yeah, I always ask them, you know.
Mm.
Yeah.
So I think you have experience in China for almost than 10 years, right? You come back to China. So can you compare a little bit about the students in your group, either in CAS or in your new university, and with the students in US, like your classmates or something? Yeah, what's the big difference? Because we're fighting for the world-class university, right? We need world-class students.
Right, yes.
Yeah. You just tell us what the world-class students it is.
I don't know. So there are many differences. I think culturally there are many differences. I mean, I can talk for 7 days and 7 nights about differences. But okay, there's maybe one major difference. I think is I think the Chinese students are very good at completing tasks.
Mm-hmm.
So if you tell them to do A and B, in the form of go open that door, pick up the luggage on the third chair and open it up. And there is this little tool that is red. Take it out, bring it to me. They can do it very well. They will not take out the yellow tool that's sitting next to it. That's.
I never think about taking the yellow tool.
No. The American students, however, when they tell you that, they go in and then they come back and tell you that this yellow tool is very good. It's much better than the red tool, That's the major difference,
How about the Sweden students, Jigang?
Actually, students in Sweden, the student is quite shy, I have to say.
Okay.
The male student is very shy, but the female is very popular. They want to try to do the things, but they want, but if they devoted to do something, they do very, very carefully. They do very, very on schedule. And if you want to do something, they will provide schedule tomorrow, Friday, something very, very detailed. They follow everything to very, very nicely. I think I'm very impressed with some of my Swedish students. They do very, very nice schedule. They do everything protocol is very particular. I think it's very, very impressive, I think.
Okay. Oh, that's very interesting because normally we see the most innovative education was in the north part of the Europe. Yeah, like Sweden, Denmark, and all these countries. Yeah, they say that the education is teaching very well for the student to do the innovative job. I think the first part is to make the schedule very good, right? Yeah, just to take what they want. Yeah, I saw this similar, very similar, characteristics. The student from Germany and Japan. Yeah, the German and the Japanese students always do very good plan. And they never, say immediately, I like this or that. But after they think over, okay, they make a very good schedule and they do very dedicated job. Yeah, that's very good.
Actually, in Sweden, we spend as supervisor, you spend most of the time to convince him. It's a very nice work. It's a very brilliant work. And we give them a lot of hopes. If he choose you, if he chooses you, he will do very, very nicely. I think this is my case.
That's interesting. That's like, Xingyu said we can talk overnight, to talk all this difference. But now I think we deliver the message to the students. Yeah, if you want to choose a very advanced topic, very good, professors, you must be very aggressive, Yeah, to all this topic and aggressive to learn new things, aggressive, to communicate with others and also, okay, yeah, you need to show, you are very active, from inside, not always push outside, right? If always pushed by all the examinations, tests, okay, it's hard to find the best supervisors, the best professors, because all these teams are never luck about students. They just choose the best one. Yeah, the most suitable one. Okay, yeah. Thank you all of you. Yeah, for this nice, panel discussion. I think time is almost up. We should move to the second part of our talk. Thank you, Xingyu. Yeah. So, Zhigang. Yeah.